Thank you. And yes, thank you guys for letting me share my ideas with you. I've been visiting for a couple of weeks. It's been nice to get to know some of you. Yeah, so today I wanted to talk about a couple of my papers about integrability, and specifically integrability around the realm of the KdV equation. The main sort of point I want to get across at the end is what the full nonlinear chiral algebra that many 2D CFTs have can buy you. Okay, so hopefully I'll be able to explain how that works. So I have this kind of vague title, where is the KdV equation? But before I tell you this, maybe I should say what is the KdV equation. And I thought I'd give you a little bit of a history lesson, because the KdV equation has so many twists and turns. It's a pretty old subject. So the story begins in the 1830s. A Scottish engineer, John Scott Russell, was studying water waves. I think he was trying to learn or understand water waves so that he could design his boats. And what he would basically do is he found like a very long and straight canal, and he drug boats down it with horses with ropes tied to the boats. During these experiments, he observed a particularly interesting wave, a wave that would travel for 1 to 2 miles without changing shape or changing velocity. And he thought that this was a particularly important phenomenon, and he called it the Great Wave of Translation. Well, nowadays it's called a solitary wave. But unfortunately, at the time, this observation was kind of downplayed. At the time, it was believed that water waves could not preserve their shape, even theoretically, without friction. And so there was several decades where many people didn't even bother to try to explain this phenomenon. But eventually it started in the 1870s, and finally in 1895, Korteweg and de Vries, they found a very simple equation from general principles. So if you assume that the fluid is incompressible and irrotational in a rectilinear canal, you can derive this equation where eta is the height of the wave above the equilibrium, we're also assuming that we're in the long wavelength limit, and the height above the equilibrium is very small. You get this equation, and it has some nice exact solutions. This is one of them, and this is the one that describes the wave profile of the solitary wave that Russell observed. And it has all of the properties that Russell had experimentally observed.
And h is the depth of the canal.
Yes, h is the depth of the canal, exactly, yes. I think, yeah, g is what you think it is. Alpha, I think, can be arbitrary, and sigma is related to the surface tension of the water. Yeah, also there's some periodic solutions that obey like a sphenoidal profile. It looks like this. Okay, but so that was about as far as it got in the 1800s. Nowadays, the KdV equation.
Sorry,
yes, go back.
That C there, is it related to alpha? Or?
Oh yes, C is related to alpha, but C can be basically an arbitrary. So C describes the velocity of the wave, right?
But is it determined by these constants, which appear on?
It is it's an arbitrary number. So
all right. Okay.
Yeah.
Yeah. Okay.
So basically, you assume that eta depends on one variable, x plus ct. And
But there is no c equals 0, then the solution is 0, right? So.
oh, yes, maybe I made a mistake when I wrote down this.
Well, that makes sense. You wouldn't expect that it would be.
No, it does make sense, but you would maybe expect there to be some alpha dependence. I think I solved this when alpha is 0. It didn't ultimately matter.
But the system is not goodly invariant, right? So it's not obvious there will be a solution with arbitrary.
It actually does have a sort of nonlinear Galilean invariance. So if you perform a boost, you also have to raise the height of the wave.
But a priori, it's not obvious that there should be a wave with arbitrary velocity, right?
That's right. That's right. Okay, so nowadays you can the KdV equation takes this simpler form. You replace eta with u, and you work in dimensionless units, and the subscripts indicate partial differentiation. And in the advent of computers, some people decided to simulate solutions to this equation, and the question that they were trying to answer was what would happen if you had two solitary waves that were traveling with different velocities, and they were allowed to evolve according to the KdV equation. And since this is a nonlinear PDE, and in general things are wildly uncontrolled. And the surprise was that it actually is very controlled. So this is a sort of a video or cartoon of one such simulation. And the solitary waves essentially pass through each other unbothered. There's a slight window where they non-linearly interact, but after they pass through each other, they retain their shape and velocity.
It looks like they're delayed a little bit. Is that what the two superimposed shapes mean?
Yes, so the
collision?
The blue, I don't know if you can tell the colors, but there's a blue and an orange plot after they collide. Those are like the solitary waves as if they weren't interacting at all. And the purple profile is the full solution to the KdV equation. And yes, there is like a slight spatial separation, but otherwise everything basically is, at least asymptotically, the exact same. Like their wave profile is unaltered. They have the same velocity. Yeah, good. So this was kind of unprecedented. It seems like these waves obey a sort of generalized superposition principle. This is something that you only expect in linear differential equations. And so
the faster one gets advanced, right?
Yeah.
And the slow one gets delayed. It's counterintuitive, right?
Yeah. Maybe you can calculate that.
Bounce into it from behind. So.
Yeah, it's a donation. It's a donation. The slower wave, the faster wave donates to the slower, and the slower
No, it's
becomes
the
the
other way around.
fastest.
In
No,
the
faster
visual, it
way-
looks like the opposite.
Faster wave goes even faster, right?
Yeah.
You see,
The slower it donates.
Huh?
The
the,
slower it donates.
The slower one.
I think
The slower one donates.
it bumps
to the
from
faster
behind,
one.
but it gets accelerated as a result of this
Right,
bump.
I see.
That's a bit weird.
The slower becomes the
No, wait. Are there waves?
The slower
dash
becomes-
lines or
Because
the
orange, that's how it would be
Slower.
propagating if it were free.
So dash line is how it would be.
Yeah.
Like for instance, orange how it would be if there were no
Becomes the larger
slow,
one.
and it's
I
behind.
don't know.
okay.
Yeah.
I guess
The
it's
blue-
words. Anyway.
So it's a bit weird, right?
yeah, it is weird. But somehow after they separate, they still have yes, there was some sort of acceleration, but after they separate, they have the same velocities as they did initially.
Yeah, but there is a time advance rather than time delay for the.
Right. Maybe, I'm not sure, but it looks sort of like the center of mass of the two solitons stays the same. But yeah. Okay, so So this is basically the origin of the term soliton, where because these solitary waves seem to like be infinitely stable even after collisions, they don't change their behavior. They almost behave like particles, so they coined the term soliton. And at the time, people were pretty confused by this, and they wanted to understand why this nonlinear PDE has this property. And after a while, after a year or so, people started discovering that this equation has many conservation laws that it implies. So I think there was actually a period where there was a series of papers by different authors finding new conservation laws. And these are the first three non-trivial ones. Eventually, people discovered that there are actually infinitely many. Okay? And somehow these infinitely many conservation laws sort of stabilize these solitary waves. So these infinitely many conservation laws is related to integrability. And by integrability, I mean I sort of mean in the Liouville sense of when you have a Hamiltonian system with n degrees of freedom and you have n mutually commuting charges in the Poisson sense. In that setting, you can find a canonical transformation which brings you to coordinates that are linear in time, so it's in that sense solvable. For systems like this, where you have when you're talking about a Hamiltonian system for a field rather than a coordinate, there's not really a sense in which there's finitely many degrees of freedom. There's more like infinitely many degrees of freedom. So this integrability notion is a bit ambiguous. But we can sort of put it on slightly more concrete terms, because this equation admits a Hamiltonian formulation. So you can write the KdV equation like this with a particular Hamiltonian and a particular Poisson bracket. And these conservation laws that I told you about imply infinitely many commuting charges in this sense. Okay, and these charges allow you to exactly solve more general the KdV equation for more general initial conditions. Like you can solve this exactly for n soliton configurations, not just 2 or 1. Schematically, you can think of this like the procedure for solving for these solutions is if you have initial conditions with like n far separated solitary waves, you need roughly 2n minus 1, I think, charges from here to reduce this PDE to a first order ODE. And once you get it to a first order ODE, you can kind of just declare that you've solved it, right? Because those are pretty simple. But there are more explicit solutions to this equation using the so-called inverse scattering transform. So it's in this sense that this equation is integrable, and normally for two-dimensional systems, we call just any equation that has infinitely many commuting charges or symmetries integrable.
So let's say it had 10 to the 80 conservation laws,
Yes.
and that's it. How would you see the difference?
So eventually, if you went up to like 10 to the 18 soliton.
So it would be related to the number of solitons?
Yeah, so eventually you would not be able to use the charges to solve the equation analytically, or exactly. Right? Of course, the notion of solving an equation is a bit arbitrary, because you can always solve an equation numerically.
But you tie the number of solitons to the number of conservation laws for large n? Is that the statement?
Yeah, so that's kind of how I look at it, where, it depends on the types of initial conditions you have, and for certain types of initial conditions, you need more charges to like nail down an analytic solution. In terms of the values of those charges, right? And if you have finitely many, if you eventually, it'll be much harder to solve the equation. Yeah. Okay. Thank you. All right. So let me see. So of course, the KdV equation, it's nice, it's simple, but it's not relativistic. And it would be interesting to see if there's some relativistic equations that have infinitely many symmetries. Maybe we can use them to understand things. Of course, there are many such integrable models, of which these are just a few. And the KdV equation, like from the 60s, was kind of used as a testing ground for developing techniques for establishing integrability, and also using developing techniques for solving systems with those types of symmetries. And you can use those techniques like the existence of a lax pair that establishes integrability to demonstrate that all of these models are integrable. Right. So exactly. Yeah. So these are, of course, in 2 dimensions, not in our 4-dimensional universe, but they, because they're integrable and exactly solvable, they provide like a really nice, useful laboratory to understand some good non-perturbative features of quantum field theory, like bosonization, J-invariant mass generation, some non-perturbative analytic properties of scattering amplitudes. These also have, even though that they're 2D models, they do have connections with 4-dimensional theories. You can find these models within 4D gauge theories. You can also, many integrable models appear in string theory as well. And even though the KdV equation is not relativistic, it still has it still pops up everywhere. It even shows up in more fundamental settings in 2D quantum gravity. So these things, you keep finding them. Okay, so what I want to do is I want to ask, out of all of these integral models I showed, the KdV equation is kind of, the first example that was widely studied. And I want to ask if the KdV equation is really that special. Like, was it an accident, a historical accident that we found this first? So what I want to do is I want to slightly generalize the KdV equation and just have some, something of this form, but with some potential v that's some other functional of the KdV field u. And of course I want to keep it having a sort of Hamiltonian formulation, so this potential is related to a Hamiltonian, and there's some Poisson structure. And I want to ask what types of equations of this form are integrable, in the sense that they have infinitely many commuting symmetries. It's not hard to figure out that any potential that is just a function of u itself is integrable in this sense, because any f and g that just depends on u and not any derivatives commutes with another potential of this form. So that's a pretty large space. But I think for most people, we want to consider systems with where v depends on more derivatives. And let's say that v depends on two derivatives or less of u. It's known that this type of potential is integrable only when the exponent here, n, is equal to 2 or 3. And when n equals 2, that corresponds to the KdV equation. And when n equals 3, that corresponds to, people just call it the modified KdV equation. Okay, but any other power does not actually satisfy this property that has infinitely many commuting symmetries. So that once you add the extra derivatives in the potential, things get more constraining. Now I just said that things get more constraining, but actually as soon as you find a potential of this form that admits an equation that has infinitely many symmetries or charges, there's actually an infinite hierarchy of potentials that also are integrable. So the one corresponding to the KdV equation also has an infinite sequence of potentials that also generate integrable equations, just showing two extra ones. And also the one corresponding to the modified KdV generates an infinite sequence as well.
By generalize, you mean you add q's? You just add q's to h?
Yes, so there's a recursive procedure that you start off with this potential. There's some operator that you can act on, v.
You can always deform v by q. No? The Hamiltonian can be deformed by one of the q's.
Yeah. In fact, basically you replace the Hamiltonian with one of the q's.
So these new potentials, they're related to q's?
Yes.
Or
Yes.
the original theory?
Yes, exactly. So maybe it'll be useful to see. So for instance, this for the KdV equation, this h itself is a q, and basically how you arrive at the rest of the equations is by taking one of these q's and calling that the Hamiltonian, right? Because all these mutually commute, you can pick any of them as your Hamiltonian, right? Exactly. Good. Okay, so really what I'm going to be asking about is like, how do I constrain this entire hierarchy of integrable equations, not just a single equation? Okay. Now, of course, there's actually a lot of literature on this in the mathematical side. There's classification theorems where you use the existence of something called a formal recursion operator that satisfies this equation where I don't add details here, but V star is some operator associated with a potential. And it's known that if a theory is integrable, it has an operator like this, and you basically use this necessary condition to derive constraints on the potential V here. And there are some really great results at third order and fifth order, which constrain the set of equations of this form to a finite list of equations that are integrable. This is like up to so-called almost invertible transformations. So if you can connect an equation to be of this form by some field redefinition under some class of field redefinitions, then that is also integrable. But this doesn't count for all possible order 3 and order 5 differential equations of this form that are integrable. A full classification of these types of equations is still unknown, and even less is known for higher order. Okay?
This is classical always, right?
Yes, this is, yeah. So
So
basically,
so one question, let's say when one goes to quantum mechanics, one could be worried that maybe there is an anomaly and that some of the Q's don't commute with each other, for example.
right.
So does this happen?
Yeah, so quantum mechanically, this is a good question. For the nice integrable systems, the charges do get renormalized by quantum correction. There is actually no anomaly for most of these situations, for the situations that I know of, at least. And they get renormalized, but they still commute. You can show.
So this KdV model with the Hamiltonian that you showed, does it exist quantum mechanically? It seems like a little dubious because it has an unbounded from below potential.
Yes.
It has like a cubic potential, right?
Yes, that's a good point.
Usually we would say that these models don't exist quantum mechanically.
Right. Okay. So I guess I was thinking of the what the statements are for the Lorentz invariant integrable models for like sine Gordon.
Yeah, those exist actually.
Yeah. And at least maybe I'll have a point explain, but
No, classically it exists because the solitons are just conserved, they don't run away.
yeah. Maybe at some point I'll be able to explain that the sine Gordon model, like the symmetries of the sine Gordon model, you can also associate equations of this form too. If you're just strictly talking about the symmetries on their own and not the stability of the quantum theory, you can still ask whether or not these symmetries or charges get renormalized. For the KdV equation and the symmetries associated with KdV and sine Gordon, they do get renormalized, but you can still find a set that commute. But yeah, that doesn't address the stability of the theory. Okay. All right. So I want to try to attack this question of classifying these types of equations. To do this, I'm going to go take a pretty sharp turn and talk about a different theory, which is a very simple one, which is just the 2D free scalar. Okay, so of course this is a free theory. It's also a conformal field theory. Here I'm writing it in Lorentzian signature with light cone coordinates defined that way. The equations of motion are the wave equation, and you can split up the solution space into left moving and right moving modes, right? Among the symmetries of this theory, right, there's a left moving shift current like this, right? It satisfies a continuity equation here. There's also a stress tensor, of course, and there's a local stress tensor which generates a Virasoro algebra. There's lots of symmetry. But what I want to focus on is just the fact that we have a left-moving current, right? Something that basically, by the equations of motion, only depends on x minus and not x plus. This actually implies a huge space of symmetries. Right? Any function of j still is left-moving, right? It's still just a function of x minus on shell. And so j squared, for instance, is the stress tensor. That's left-moving. J cubed is also left-moving. J to any power is left-moving. So this generates an infinite number of symmetries, or currents. In fact, any functional of j, so L depends on j and its derivatives. So here the subscript I just indicates the maximum derivative I of with respect to x minus of j that this functional depends on, and there can also be some explicit x minus dependence. This is also left moving, right? And this is a current that generates a symmetry. Okay, and it's a nice calculation. And also, I should emphasize that this is all classical. When you talk about these arbitrary functionals, it's a little bit, you can do it, but it's a, you have to care about point splitting when you define the composite operator. But classically, you don't have to worry about this. It's a nice calculation to show that each current of this form generates a symmetry of this action. It's invariant under this infinitesimal change where this E operator acting on the functional is called the Euler operator. It's a linear operator which gives you the Euler-Lagrange equation of this functional as if it were like a 1D Lagrangian. Okay. So yeah, this is the full space of symmetries. And okay, so one property that I'm going to be using of this Euler operator that's useful is that if the Euler operator acting on L is 0 for any value of j and its derivatives, this is equivalent to L being a total derivative. Okay. So we'll see why I'm mentioning this in the next slide. Okay, so let's try to understand this space of symmetries and see what the Lie algebra is associated with this. So if you just take the commutator between any two such transformations associated with two functionals L and L prime, you get a new transformation associated with the functional L double prime. And you can figure out that L double prime takes this form. So this defines the Lie bracket of this algebra. Now, this is a, so right, I guess I should emphasize that this thing on the right-hand side is still a functional of J. And so this algebra closes on the space of functionals. For instance, the Virasoro algebra is a subalgebra of this, and various other chiral algebras that people study are a subalgebra of this. But this is like the entire chiral algebra associated with the free scalar, the classical free scalar.
You see Virasoro here, I slightly doubted that. I assume you mean the Witt algebra.
Oh yes, sorry, yes, I meant the Witt algebra. Thank you. Yeah, so if you quantize this, then you do get the Virasoro algebra out of this. But yes, so basically one way to see the Witt algebra is like x minus to the n of j squared is your generator. That's how you define the modes of the stress tensor. Or x minus to the n plus 1, I think, of j squared. And those generate the Witt generators. Thank you. Okay, so a useful thing to mention is that there's this, or to define, is this equivalence relation. So because I mentioned earlier that the Euler operator acting on a total derivative is 0, that generates a trivial transformation. So I want to mod out by those types of functionals. So I'm going to define this equivalence relation. So L prime is equivalent to L if they're related by a total derivative. Right? I also, it's useful to define something called order, which the order of a functional n, it's the minimum possible highest derivative of j that Ln depends on by adding total derivatives. So as a very simple example, this minus j times j sub 2, remember, maybe I didn't mention this, the subscript indicates the number of derivatives acting on j. So you can reduce this to just depend on one derivative, first derivatives of j by adding total derivatives. So you would call this thing an order 1 functional. Okay. So, okay, now I have this giant Lie algebra. What do I want to do with it? I want to understand the structure of it. What are the subalgebras? In particular, I want to see if there are infinite dimensional commuting abelian subalgebras, right? So let's suppose I have such a subalgebra, an abelian subalgebra that's infinite dimensional. So a sequence of functionals, lni, where I just counts the, or orders the functionals in some way.
Sorry, but classically you will have, right? Because you have the loop algebra as well.
Mm-hmm.
So this is.
With the algebra.
No, but not with algebra.
Oh, the
with
calculus
algebra
is,
non-centrally extended as well. I'm talking about the Kakmoody non-centrally extended. That's the loop algebra, and this is abelian and infinite dimension.
Yes, that's true, but I'm not sure if that exists in this. Sorry, no. Yes, you can also define
It's like
modes.
a Kakmoody with k equals 0. Right? That's
Yes.
infinite dimensional. And
Yeah.
so you one hat sub 0. That's algebra is infinite dimensional and abelian.
Right. Yeah, so that will define one such abelian subalgebra that will help us write out integrable deformations. But there's a more general class of abelian subalgebras that I'll be studying. Yeah.
This is more general functions.
Yeah.
Well, another example would be the mixed term between the linears one, the loop algebra, and the width one.
Mhm.
K equals 0 is also abelian,
Okay. Yeah.
infinite dimension.
Right. So exactly. And I think you can also, whenever you have a with algebra, or even quantum mechanically, the Virasoro algebra, you can define a set of commuting charges. So that this will be similar to those types of constructions.
Probably there are much more. Okay.
Yeah. So yeah, good. So let's say we have such a abelian subalgebra. It is the case that for every such subalgebra, there is an integrable deformation of the free scalar of this form. So if you add a deformation, which is invariant under all of these, and basically you can pick out any of the functionals in the subalgebra and add it to the action. And this action is invariant under all of those symmetries. Okay.
It's not Lorentz invariant.
It is not Lorentz invariant. Most of these are not Lorentz invariant. These specific types of deformations are never Lorentz invariant. But for some subalgebras, there are also other integrable deformations that are Lorentz invariant, which I'll show. But most integrable deformations are not. Yeah, just like the KdV equation. Okay, so yeah, so I'm not going to show this, but you can show that this action is invariant under all of these generators, these currents or symmetries generated by the currents. And so this defines an integrable model. Okay, so why is that important for the KdV equation? So if you look at the equations of motion of this, it takes this form. And if you just relabel things to go back to the conventions of the KdV equation, so x plus you identify with time and x minus is space, and you say that J is the KdV field U, it gives you this general type of equation where this potential is related to the generator, one of the generators of the symmetries. And in general, it will take something of this kind of form. So some thing which is quasi-linear in u of derivative 2ni, and could have some arbitrary dependence on the other derivatives. Okay. So what I've done is I've reduced the problem of finding integrable equations of the KdV type to an algebra problem, where I'm just taking the commutator and trying to see what types of functionals set this to 0. Right, yeah.
So there's some interpretation of this in terms of the Fock space, right? Because you have the bosonic Fock space of the KdV equation, right, or any integral hierarchy, and so is your result somehow relating the Fock space of the free scalar to the integral hierarchy?
I'm not sure. I'm not exactly sure how to think about that. It's a good question. I think each deformation defines a different theory, and I think, you know, if you were to try to study, this discussion so far has just been classical, so I'm not sure how to think about the Fock space. You know, the KdV equation is nice because you can kind of construct a set of configurations that correspond to like particle-like configuration. But it's not necessarily the case that the other ones will have a similar interpretation in terms of.
So isn't that pretty generic to integrable hierarchies that you can
Like having a Fock
sort
space
of,
description?
like that you can find this? Maybe I'm wrong, but like certainly for the whole anything in the KP hierarchy, you can find a similar bosonic Fock space, right?
Yeah. So this is true. I think I'm not sure how to think about it for this more general set of theories that I'm defining, because you'll see later that the theories are pretty exotic and quite nonlinear, and yeah, so I'm not sure. Thank you for the question, though. Okay.
But when you have a finite number of degrees of freedom and the system is integrable, you can find action and variables. Right? So the Q's are action in this case, but are there also the angle variable? And then you can define a canonical Poisson.
Yeah, so I think these types of this type of interpretation is like, it's not clear that it's always guaranteed, but you can use these charges to find some kind of canonical transformation of that type that you're thinking of. But certainly for like the well-known cases, like the KdV equation, there are like these transformations that you can properly interpret as like transforming things to action angle coordinates, like the so-called inverse scattering transform of the KdV equation. And I think you can do this for the Sine-Gordon model as well, and other well-known integrable models. But yeah, more generally, I'm not sure how to, if there's like a general theorem that this is always guaranteed for these systems with infinitely many charges rather than finite degree of freedom systems. Thank you for okay. So how much time? Okay. So what I want to do is I want to basically just search for a sequence of functionals that satisfy this equation. That when you take the commutator, this transformation is trivial. Okay. This is a pretty maybe if you remember how the Euler operator looked. This generates a very complicated set of equations for these functionals, but they are ultimately like a bunch of differential equations that you can impose on these functions that you can solve. Okay. So before I get into like actually systematically solving this, I'll just show like some simple examples. So this is, for instance, a set of functionals. You don't have to see the exact form of this or look at it too hard. But these are the functionals which are associated with the KdV hierarchy. You can show that all of these commute in the sense that I'm talking about with respect to the re-algebra that I showed on the previous slide. Right, so if you add to the free scalar, the simplest functional, this generates the KdV equation. Okay, and the rest of them generate the higher KdV equations. There's a couple others that are well known, subalgebras that are well known that are.
Can you check them? I missed the last.
Yeah. Yeah. So for this particular way of writing the KdV equation, it has this type of.
I just couldn't see where the 6 comes from.
Oh yes, yes, because you have this cubed here.
But then, okay, I got it.
Yeah.
Then,
Good. Okay.
thank you.
So the next slide are just the other 2 examples that are well known. But basically, I'm showing you the subalgebras that are polynomial functionals of J and their derivatives. And there are 2 subalgebras that are basically compatible with Lorentz invariance. So these are the ones that have definite scaling under boosts, under 2D boosts. So this sequence of generators, they define KdV type equations, but they also, this subalgebra admits Lorentz invariant deformations of this form. So if you add this to the action instead of the type of interaction that I was discussing, this preserves these symmetries. And these are the ones that correspond to Sine or Cinch-Gordon or the Liouville model. Also, this functional, if you add this to the action, this generates the modified KdV equation, and the rest of them, the higher modified KdV hierarchy. Then there's another.
So the thing in the exponential, the 2 is something you can absorb? Or
Yes.
does it check you can absorb it?
Yes, yes. You can redefine things so that it's just e to the phi or e to some other number.
So it doesn't. It's not important what the.
Right. It's not important. It's just that this is the specific number that leaves these specific functionals.
I thought you were deforming by the L's. Now you're doing something else?
Yeah. So that's right. So in general, the deforming by the L's is always guaranteed, but for these special subalgebras, you have these extra deformations.
Okay.
Yeah.
And these extra deformations are nice because these are Lorentz invariant, and the L's generally generate things that are not.
Correct. Yes.
But the fact that this extra deformation exists, how do I see it?
Yeah, so it's a little unclear, like just by looking at these tedious formula.
Right.
But yeah, if you just worked out like what these symmetries, so each one of these generates an infinitesimal symmetry transformation on phi, and you can show that with this potential, it is also the action is invariant under those infinitesimal transformations.
So why don't you call this VL0? Isn't that like part of the sequence? It's not some L0?
I would. So the L's are strictly functionals of J,
Okay.
whereas this is, I guess it would be like a non-local functional of J, I guess, in some sense.
Still back to the question, because on the other potential you emphasize 3 and 6.
Yeah, yeah.
Uh,
So it could have been
could
1
it
and
be
2.
2 and 4, for example?
Yes, yes.
Okay.
Yeah, so it was just, I put the 3 and the -6 just because for this list of functionals, this is left invariant by these. But you could rescale things so that you change the scalings and the exponent, as long as the relative scaling.
That's what I say. So 2 and 4 would do the job.
Are these the only extra deformations that are compatible with this symmetry?
Yes, that is proven. So that's it's proven that any well, maybe it's not the only, but this is the these are the only 2 potentials that just depend on phi.
There could be a dependence on j and phi,
right.
like j square e to the minus 7 phi.
Right.
Something.
But it might be hard to make that compatible with Lorentz invariance. But yeah, so these are the only ones that are allowed for integral definitions of this
So you
theory.
could just take products.
Products of j with,
Yeah, yeah,
with the
yeah. This is classical.
yeah.
How many of these invariants are, how many of these preserved charges are expected to persist when you turn on quantum corrections?
Yeah, so all of these persist.
And for this, yeah, so this is, I think, is no, but for this Taiteka model.
Or yeah, sometimes people call it the Bulloff-Dodd model.
How? What was the name?
I didn't dare to ask.
Dodd or below Dodd. I'm not sure how to.
Below Dodd? Say again? What?
I'm not sure if I'm pronouncing it correctly. Bulloff-Dodd. It's two names.
Below Dodd?
Bulloff and Dodd.
No, I didn't.
Do you recognize these names? Or?
I've never heard this before.
Okay. I think these are like British mathematicians. But,
So what were you saying about the second model in terms of quantum correction?
yeah, so I'm actually, yeah, I'm not sure what the story is for the quantum corrections for this.
It looks like a strange model because the B operator is highly
Yeah.
relevant.
Yeah.
Mhm.
It's just weird. No? Fine.
Yeah.
Yes.
I mean, it's,
You could, I guess,
it's not, also not normalizable. It's exponents to it.
you can think of it from the perspective of the integral bootstrap, where you're like bootstrapping interactions that generate a scattering amplitude that properly factorizes. And if you demand that there's a phi cubed interaction, and then you keep getting the rest of the higher order interactions, then you'll generate this potential. But if you set the cubic interaction to 0, then you get this type of potential generation.
Here the scalar is not compact, right?
Yeah, I guess you want to think of it as non-compact.
So it's some variant of the Liouville model
Yeah.
that I've never seen before.
It's
Is there like an integral S matrix?
Yeah.
Oh, there is for this.
Instead, if you start without assuming phi to minus phi symmetries, you start phi cube and just bootstrap what kind of how to get factorizable
Yeah.
amplitude.
I said here there is an exponential wall on both sides. Is there an S matrix? It looks like it doesn't look like.
Yeah, this operator looks too non-normalizable.
It looks like there is an exponential wall from both sides. Does this model actually exist?
Well, it's integrable model.
maybe you could say the same thing about the Lulu model. But-
Liouville is
but-
one side wall.
Right.
No?
Yes, yes.
There is a scattering problem. Here there isn't.
Oh, I see what you mean.
Yeah, it's like more like a bounce type
But
problem.
you could, I think there's a parameter you could take loop B to be 0.
Yeah, yeah. A and B
You could take B to 0.
take a different linear combination of
Back to the other model.
No,
Back to the
but
previous
already
one.
Singe Gordon has this property.
Yeah.
So, but
It's more like a bounce type problem, not a scattering problem.
no, but it's
It can be a
it's
model
QFT
without
scattering,
being
right? It's not a potential for it's not quantum mechanical potential. It's filtering potential, so that's why that's a problem.
Okay, maybe since I'm starting to run out of time, I should keep going. I probably won't be able to finish the talk, but I can say a few things, or just the main statement.
Sorry, but where is Singe Gordon here? Because your things are already. There should be some eyes. Possibly.
Yeah. So I was saying you can. There's some freedom when I'm writing this subalgebra. Like you can rescale things. You can change J by some affine transformation, like J going to A, J plus B, where A and B are some complex numbers, and you still have a commuting subalgebra.
I see.
And so you can rescale things so that there's an I in the exponent, and that there's also a subalgebra associated with that.
It's weird that the second model doesn't appear in the HepKH literature.
No, I think it does.
What's
There
the
is
name
this
of it?
lectures by Dore on integrable S matrices. And I think he mentions he uses that whatever second name.
Yeah.
So
People love
Have
that.
people study TPA?
I don't know, probably.
UV limit, presumably it's not well defined. Otherwise we would know.
So you have 2 minutes, right?
Yes. Yeah. So let me try and summarize the statements. So to be a little bit more systematic, you can say a few things about these subalgebras. So if you try to solve this equation, right? This equation is demanding that these two functionals commute, and you can expand it in terms of derivatives of j, and in general, it'll be a polynomial in some higher derivatives of j. And the coefficients in front of each monomial has to be 0. And so the simplest one here is this coefficient of this monomial. And this has to be 0. Right? So this defines some differential equation. So it's coupled with ln and lm. Now, if the order, so these subscripts indicate the order. If the order, if m is greater than n, then you can solve for lm, at least part of it. So it's dependence on jm has to be quadratic, and then there is some undetermined functional of order less than m. Okay. If the two functionals are of equal order, you can basically determine that these functionals must be the same, or must be proportional to each other. So, so if you just rename this as ln prime, it must be proportional to the other functional plus some lower order functional that's undetermined. But this must also commute with ln, and so since this is an algebra, you can take a different basis and remove this. So in such a subalgebra, all functionals. In such a subalgebra, you can find a basis for which there's a single functional of a given order. Okay, so that's kind of the structure. And so this is how they kind of set up. So there's going to be some sequence of functionals with monotonically increasing orders. And there's going to be one functional of a given order. There's a set of order 0 functionals that all of these commute with, like the stress tensor and j. Then there's going to be some, the smallest non-zero order functional, which is undetermined. But then the rest of the functionals that are of higher order than this one have to have this kind of dependence on their highest derivative of j dependence, right? So this is kind of how they set up. So the point is that this functional, so all of them have to be quadratic in their highest derivative order of j. But this one can have, in general, some non-quadratic dependence on j and 1. Okay, so maybe I'll just flash the. So the question is, what kind of non-quadratic dependence on the lowest order functional is there? And here's some examples where if you try to solve this, you get these types of sequences, which are quite odd. And you can just see what types of equations that they generate, and they're very strange. Right. Sorry, I'm trying to get to the point so that you guys can eat lunch. So let me just say what the result is. That as far as the non-quadratic dependence that ln1 can depend on, you can phrase it in terms of the following constraint, that ln1 must commute with this functional, where now the primes indicate the number of derivatives of ln1 with respect to jn1. And so the fact that they commute means this. And you can figure out what that determines on the functional, and it tells you that ln1 has to satisfy this transcendental equation. Okay. And for different values of the orders, when n1 is equal to 1, you can invert this and get this specific solution, where a and b are undetermined functionals. For n1 greater than 1, this is hard to invert, but you can find a special subset of them for which you can solve exactly, and you get this dependence. Okay. And maybe since I'm actually over time, I should probably just end here and not try to justify the result.
Actually, one question. So all your generators commuted, they were a set of infinite commuting charges. So I missed what's special about these algebras are not, are they subalgebra of the algebra you already had or not?
Yeah. So these are subalgebras of the giant nonlinear chiral algebra of the.
But then aren't they automatically commuting because they are part of a commuting algebra?
Oh, sorry. So the chiral algebra of the free scalar is not abelian. There are right. So the Virasor, or sorry, I keep saying Virasor. The Witt algebra is a subalgebra of this, which is not commuting.
So that hierarchy that you showed is not a hierarchy of commuting charges?
They are.
They are. Okay.
Yeah.
Then what algebra is this the subalgebra of?
This is the subalgebra of the chiral algebra of the 2D free scalar. And these are supposed to be infinite dimensional commuting subalgebras of that.
And one is of them is the KdV.
Yes, one of those is the KdV.
Yeah, but then you have more.
Yes. Okay. Thanks for the question.
So, I mean, I'm not surprised that with the free scalar you can do a lot of stuff, but what of all this story, what's the generalization to, say, a conformal theory?
Yeah, so...
And where I know that there is a Virasor algebra or a Witt algebra, but nothing else, basically.
So good. So in fact, this story is actually pretty general. As long as you have either left and right moving factorization or holomorphic or anti-holomorphic factorization, you can play this story. So if you have a holomorphic stress tensor, you can consider functionals of the stress tensor and ask what types of functionals commute with each other. And this is how you generate the, well, they call them KdV charges in the 2D CFT literature, but they're composite operators of the stress tensor. And
built from the Virasor generators.
Yes, built from the Virasor generators. So that you can do in a generic 2D CFT with the stress tensor. But you can also do this if you have other types of holomorphic currents, like the WZW models. You can ask this question and study the nonlinear chiral algebra and find commuting subalgebras. The problem's a little bit harder, but you can do that. You can do this for free fermions or even for some massive theories in Euclidean de Sitter space.
And now, again, how much of this survives quantization, where instead of Witt you have Virasor, for instance?
Yes, so in general, it actually, I think I have a backup slide. The algebra deforms massively quantum mechanically, so there's infinitely many quantum corrections. So take alpha prime and BH bar. And this is the algebra, the full algebra quantum mechanically. Generally speaking, what seems to happen is that the functionals that are polynomials, the abelian subalgebras seem to survive. I don't know about the Tsitseka or Beloff-Dot model, but at least for the KdV subalgebra and the Sine-Gordon, these survive quantum mechanically. For the nonlinear ones that I was just describing very quickly, those do not, those get altered kind of badly quantum mechanically, so they increase, so at least you can try to compute alpha prime corrections to the charges to make them still commute. And the first alpha prime correction to the charges increases the order of the charge in derivatives of J. So in principle, you'd expect that at finite alpha prime, these become non-local charges, but if they still persist.
That's interesting because you say they could be related to this non-local integral charges. That was important, to argue for integrability of S-matrices. Is that right?
Yeah, I guess you can argue for integrability if you have one non-local charge, right?
Yeah.
And so maybe this is related.
So maybe ask the related question. So we know how to get KdV charges from Lindwasser quantum mechanically. Is it true that you can kind of enlarge the set of commuting charges beyond KdV by including some of these?
Well,
because if that's the case, then because people study this, this generalized Gibbs ensemble where you refine by this KdV charges in connection to the ETH. Maybe there's a further refinement that you can do if some of these charges actually commute with KdV.
Yeah, I think if they commute with KdV is a separate question, but I guess to talk about something beyond those charges, you need a more specific setup rather than.
But I guess the mathematical question I'm asking is that is KdV a maximal commuting subalgebra of Lindwasser? If you allow yourself to consider now the more general functions.
Yeah, that I don't know actually. I mean, at least in this setting, it seems like for instance the other subalgebras I'm finding don't commute with KdV charges.
I see.
For instance, but maybe there's some other charges that people haven't found that commute with the KdV charges, but I think people have accounted for all of them.
Because the KdV charges are all polynomials in terms of their result generators.
Yeah.